The 3D scanner is made of the following components: a scanner base, 2 stepper motors, plates to attach the stepper motors to the base, a shaft coupler, a piece of threaded rod, 2 guide shafts, a carriage with associated hardware to attach to the base and to one of the stepper motors, an IR sensor, a constraining plate to keep the guide shafts parallel, a turntable to rotate objects as they are being scanned, and custom electronics to rotate the motors, read the IR sensor, and save scan values. I decided to begin with the electronics. The electronics of this project are designed around the Arduino Pro Micro. The Pro Micro is a small Arduino variant with an onboard USB connector, which is used to program the microcontroller. In addition to the Arduino, the 3D scanner contains the following electronic components: a power connector with screw terminals to provide 12 volts to the project, a push button to reset the microcontroller, an infrared sensor to measure the contours of scanned objects, an SD card to save scan information, 2 stepper driver boards to control the motors of the 3D scanner, and 2 NEMA 17 stepper motors. I first found an object I wanted to scan and attached double-sided tape to its underside. I then placed the object in the center of the turntable and plugged in the power. After a brief initialization period, the scan was underway. The time it takes to scan an object depends on the parameters in the Arduino code, such as desired angular resolution, number of scan samples per reading, and amount of time to pause between each rotation of the turntable. In this video, the object is being scanned at 1 degree turntable increments with 100 samples per reading, and a brief 200 millisecond pause between the time the turntable rotates and the IR scanner measures the distance to the object. This is a time lapse of the scan. With these parameters, the total scan time was approximately 40 minutes. After the scan completed, I ejected the micro SD card from the PCB and transferred the generated text file to my computer. The scanner information is processed using code written in MATLAB, a programming language commonly used by scientists and engineers for numerical computing tasks. This code loads the scanner data, creates a point cloud of the object, post-processes the point cloud by filtering it to remove noise, and writes the resulting point cloud to an STL file for printing. After adjusting the filtering parameters in this code to my liking, I ran the code and opened the generated STL file in my slicing program. I used the slicing program to scale the dimensions of the STL file, used it to generate G-code to print the object, and exported the G-code to an SD card. After this, I plugged the SD card into my 3D printer and printed a copy of the object. With the help of my 3D printer, I could now digitize and duplicate any object in my house. The dance pad is made out of the following components: a 35 by 35 inch baseboard, 4 1 by 35 inch dance pad borders, and 5 11 by 11 inch stationary panels, all made out of 1/2 inch thick MDF, 4 9x9-inch riser panels made out of 1/4-inch thick hardboard, 16 8-inch strips made out of 1/2 by 5/8-inch foam insulation tape, 12 metal button contacts made out of aluminum foil, 4 11x11-inch button pads made out of 1/4-inch thick MDF, some paint and laminated graphics, 9 11-inch by 11-inch clear panels made from 2mm acrylic, an Arduino microcontroller with associated wiring, and a 3D printed electronics enclosure. Let's begin by taking a look at the key electronics concepts behind the dance pad. This project is built around the Arduino Leonardo, a small, open-source electronics prototyping platform found in many of today's maker projects. The Leonardo incorporates the Atmega32U4 chip, a microcontroller that can be programmed to act as a USB input device, more specifically a USB keyboard. The working principle behind the dance pad is that the microcontroller sends out a keystroke every time a button panel is stepped on, which StepMania recognizes as a button press. To do this, the Arduino must sense a step on a button panel as an input signal. Microcontrollers sense input by measuring the voltage of their pins, and can be instructed to measure or read a pin's voltage using code. If, during a reading, the microcontroller measures a large enough voltage on a pin, the microcontroller returns that the value of the pin is high. Alternatively, if the microcontroller measures low or no voltage on a pin during a reading, the microcontroller returns that the value of the pin is low. Changing the pin voltage from high to low as a button is pressed therefore enables the microcontroller to sense input from the button. The concept that makes sensing button presses possible is the pull-up resistor. When configured to sense input, the pins of a microcontroller have a large electrical impedance that resists the flow of current, which can be modeled as a large resistor that internally connects to the microcontroller's ground. Current literally travels the path of least resistance. When placing another smaller resistor between a microcontroller's 5-volt line and one of its input pins, current will follow the wire path and travel through both resistors to the ground because it literally has no other path to travel down. As a result, the voltage of the pin will be close to 5 volts, and the microcontroller will return that the pin's value is high. If the wire between the smaller resistor and input pin is now connected directly to the microcontroller's ground line, which is at 0 volts, current will not flow through the large resistor, instead flowing only through the small resistor directly to ground because the total resistance of this path is less. Because of its direct connection to ground, the pin voltage is now also at 0 volts, and the microcontroller will return that the pin value is low. A button between the small resistor pin junction and the ground literally acts like a switch for connecting and disconnecting the ground line at this point in the circuit. When the button is not pressed and the connection between the junction and the ground line is open, the voltage on the input pin is close to 5 volts. When the button is pressed and the connection is closed, the voltage on the input pin drops to 0. Once the button is no longer pressed down, the electrical connection between the small resistor pin junction and the ground line is broken. The voltage on the pin is pulled back up to near 5 volts, since current again travels through the large resistor. In the dance pad, each button is constructed out of 3 metal plates, one which is connected to the small resistor and 5-volt line, one which is connected to the ground line, and one which closes the connection between the two by being stepped on, causing the other 2 plates to touch. While the dance pad's buttons could in theory be constructed using only 2 plates, having the plates with the electrical connections remain stationary lessens its chance of failure, since the connections do not move during gameplay. I started up StepMania and configured the button mappings of the dance pad in the options menu. I then got ready to dance. Let's see how this goes.